In this video, we're going to be solving an application of a polynomial inequality. We're going to talk a little bit about a vertical position equation because we're going to use that to solve this problem. So the vertical position equation, S of t, of an object moving upward or downward under the influence of gravity can be modeled by S of t equals -1/2 g t squared plus v naught t plus s naught, where g is the acceleration due to gravity. So that's either going to be 32 feet per second squared or 9.8 meters per second squared. T is the time of travel. V naught is our initial speed. And our S naught is the initial vertical position. So let's take a look at the example that we're going to be using here. So a toy rocket is shot straight upward from a launch pad 1 foot above the ground level with an initial speed of 64 feet per second. So we're going to write a model to express the vertical position S of t in feet of the rocket t seconds after launch. And so we're going to use our position equation, S of t equals -1/2 gt squared plus v naught t plus s naught. But we're going to have to replace those values, specifically our S naught, our V naught, and our G. From the problem, we see that we have an initial height of 1 foot above that ground level. So that's going to be our initial height, 1. It says we have an initial speed of 46 feet per second. So we can put down, 64 feet per second. So 64 feet per second. And because we're dealing with feet and seconds, that means for gravity, we're going to be able to use 32 feet per second squared. So we're going to take that and we're going to plug those values in, which gives us S of t equals -1/2 times 32 t squared plus 64t plus 1. And we can take 1/2 and times that, or the -1/2 times it by 32, and that's going to give us -16. So we're going to have -16t squared plus 64t plus 1. And this is going to be the model that we're going to use to represent the rocket t seconds after launch. From here, we're being asked to determine the times at which the rocket is above a height of 50 feet. Now remember that S of t represents the height of the rocket after t seconds. So we're going to replace that with the 50. And specifically, we are looking for above a height of 50. And so that gives us a -16t squared plus 64t plus 1 is greater than 50. So to solve this, we want everything on one side of the inequality. So we're going to move the 50 over. So that's going to give us a -16t squared plus 64t minus 49 is greater than 0. And then from here, we're going to use the quadratic formula. So we're going to have an a value of -16. A b value of 64, and a c value of -49. We're going to plug that into the quadratic formula, which is x equals -b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. So now we're going to take our values and we're going to plug those in where they belong. So I've used some colors to help us see where they go. We plug them in. And now when we plug these in, what this is going to give us is our boundary points, right? This is going to give us our boundary points. So from here, we're going to see that we have x equals, this is going to become a -64 plus or minus the square root of 960, all divided by -32. And 960 can be broken down. So to break the 960 down, we're going to make a factor tree. I've got it all the way down to its prime factors. So I'm going to have x equals negative 64 plus or minus something all over negative 32. Now we just got to figure out that something. So we're looking for groups. We've got a group of 2 here. So that's one group of 2. Let's give us a little bit more room here to write. Okay. And then we have another pair of 2 right here. And yet another pair of 2 here. But it looks like we're going to have this 5 and 3 without pairs. So that's going to be radical 5 times 3 on the inside. So 8 radical 15. And so that's what we're going to put here. 8 radical 15. And then from here, we're going to look at what does 64, 8, and 32 all have in common? And the answer is that 8 can go into all of them. 8 can go into 64, negative 8 times. And here we're going to have a 1, and here we're going to have a negative 4. And then as we look at this, a negative and a negative is going to make a positive. So we're going to have x equals 8 plus or minus radical 15 all over 4. And then we're going to plug these into the calculator and get a couple decimals. So if we plug in with our minus sign, we're going to get about 1.03. And when we plug in with the plus sign, we're going to get about 2.97. And so these points right here are going to be our boundary points. So we're going to set up a x-axis and our boundary points. So we're going to have a 1.03 and a 2.97. And now we need to pick some points to test. So I'm going to test a negative 1, or not a negative 1. How about if we test a 1? That's a nice number. Let's test a 1, let's test a 2, and let's test a 3. So we're going to plug those in. And we're going to plug those in to this equation right here, right? We're plugging it into this equation right here. All right, so we're going to plug those in. So we have negative 16 times 1 squared plus 64 times 1. Let's give ourselves a little bit more room. Minus 49. And when we plug that in, we're going to get a value of negative 1. And we're going to plug it in with a 2. And we can plug that into our calculator. And we're going to see that that's going to give us a value of 15. Now we're going to plug in the 3. And that's going to give us a value of negative 1. And remember that we're looking for where are we greater than or equal to 0, which means it only happens right here at 2. So it happens between our 2 boundary points. So that means that our solution set is going to be approximately 8 plus radical 15 over 4. And 8 minus, or I guess technically the minus would come first because it's the smaller number. So you've got to be really careful. Minus radical 15. And then 8 plus radical 15 over 4. Which is going to approximate to basically saying that you've got 1.03 to 2.97. So this is what it looks like just as numericals. But because it's a word problem, how would we word that as an answer? Well, we would say that the rocket will be above 50 feet high between 1.03 seconds and 2.97 seconds after launch. And so if we take a quick little look at what the graph looks like, here we see that we've got that 50 feet, right? So we're looking for where are we above 50 feet. And we see our boundaries of this 1.03 and 2.97 seconds. And we see that that is where we are above that 50-foot threshold. And so that's how to use a position equation to help you solve an application problem for a polynomial inequality.